So let's go ahead and talk about the behavior of my polynomial graphs at 0. So the first one we're going to talk about are our odd degrees, the x to the third, x to the fifth. What these graphs show and what we can prove algebraically is that if for every polynomial function of an odd degree, there is going to be at least one real value of x that makes f of x equal 0. What that means is I can plug in at least one value of x that's going to make y equal 0. Okay, the real zeros are my x-intercepts on my graph. And if we look at our graphs, we can see where those are. So what this is telling us is my real zeros are at -3, -2, and 1. And looking at my equation, the highest exponent tells me how many zeros I should have had. We should have 3 zeros in this. 3 real zeros, or 1 real and 2 imaginary. However that works. We can't have 3 imaginaries, though. Imaginaries always come in pairs. So how that works is if you take the initial equation and you factor it so it looks like this, we can take each factored portion, set it equal to 0, and solve for x. And you will see these are the real zeros in this graph. I took each of the factors, set them equal to 0, because if any of these factors are 0, if x minus 1 is 0, 2 times 0 times x plus 2 times x plus 3 would be 0. If any of the parentheses are 0, the whole multiplication becomes 0. Now, if on our odd function, if we cross the x-axis like this, we're going to have one real 0 right there, and there's my one real 0. And then we're going to have 2 imaginary zeros. So we can say x minus 2 equals 0, so we know x equals 2. X minus I equals 0, so x equals I. And x plus I equals 0, so x equals -I. Now with these i's, normally how we would write them is we would say x equals plus or minus I, because i's always travel in groups when we're finding our zeros. So you can still see we've got one real 0 and 2 imaginary zeros for a total of 3 zeros. And then what we have on this one is we have different zeros, but they have other multiplicities. So you can see that we should have a total of 5 zeros. Well, this x minus 1 is giving me 2 of those zeros. So if we know x minus 1 equals 0, x equals 1 with the multiplicity of 2. That means 1 is a double 0. And then we have x plus 2 equals 0, so x equals -2, and that has a multiplicity of 3. Boom. And I know that by the powers on the factors. Right there it said we should have 5 zeros, and I do. 1, the 0 of 1, I can tell that has a multiplicity of 2 because it comes up, it kisses the 1, and then it just it rebounds right at that 1. And then this one just happens to give me 2, or 3, I'm sorry, 3 of the zeros. Well, what if we have even degrees? Now, even degrees, excuse me, are function along the same way. Once again, I should have 4 zeros. And you can see by looking at my factored form, my 4 zeros are x equals 1, x equals -1, x equals 2, and x equals -2. 1, -1, 2, -2. Right there, we crossed the x-axis 4 different times, and I knew I'd have 4 zeros because of the highest degree, or that highest exponent. So we can see on this one that we cross the graph 1, 2, 3 times, but we need 6 zeros. And what we can see happen is at a -1, we are going to have 2 zeros because it kisses it and it moves up. That's a double multiplicity. So the graph touches the x-axis and then turns, and the graph crosses the x-axis and changes shape at 1, 0. That lets me know that we're going to have that multiplicity of 3. So my zeros are x equals -2. That's a multiplicity of 1. X equals -1, multiplicity of 2. Because it happens twice. And x equals 1 with a multiplicity multiplicity of 3. Because 3 of those zeros, because it crosses and it changes shape. Well, this one just crosses. That's 1. But if it changes shape, that lets me know there's more than 1 0 at that point. So if we look closely at this last function, this one that we just looked at, it is a 6th degree polynomial with there's 3 different real zeros. Yet the behavior of the graph at each zero is different. This behavior depends on the multiplicity, which we have used I have to sound it out every time I say it, of the zero as determined by the exponent of that corresponding factor. So you can see what happens. So when we are looking at our zeros, if we cross the x-axis, then we have 1 0 at that x. If we come up and we are tangent, my x-axis is tangent to the curve, that gives us an even multiplicity, a multiplicity of 2 or 4 or 6. So if the graph touches the x-axis and then turns around, then we have multiple multiplicities at C, but an even amount. So 2, 4, 6, 8, whatever. And then the graph crosses and is tangent to the x-axis if C is an zero of odd multiplicity greater than 1. So what we see is the graph quote unquote wiggles at that x value. It changes shape, or not really direction. It's still going down. We're still decreasing, or we're still increasing, but it kind of flattens out. It changed shape just a little bit. Okay, so when we come back in the next video, I'm going to make this one a little quick. We're going to talk about our turning points and our end behaviors. You know, why don't we do that now? Make this one a little longer, that's okay. So our turning points. A polynomial of degree n has at most n minus 1 turning points, with at least 1 turning point between each pair of successive zeros. What that means, if I give you some kind of graph, let's say I give you a graph that looks like this. Well, we are increasing, we hit this point, we start to decrease, hit this point, and then we increase again. Well, what we can see here is we have 2 turning points. This means we need to be at least x to the third. And we know this is going to be an odd function because we have my end behaviors are going in different directions. If let's say we have a graph that looks like this. Well, we have 1, 2, 3, 4, 5 turning points. This means we need to be at least x to the 6th. At least. We could be more, because some of these might be zeros that just kiss the x-axis and keep going. Now let's talk about end behaviors. End behaviors are what happens at the extreme end of my graph. And the ones furthest left and furthest right, those are my extreme ends. And the leading term is the term that determines that. We're only interested in this value to determine my end behaviors. So when we're looking at end behaviors, we're looking at this arrow and we are looking at this arrow. So the first thing we say well, they kind of did this one backwards, but as x approaches infinity, f of x also approaches infinity. What this is saying, as x goes to the right, f of x goes up. That's what happens at the right. The more to the right we go, the graph goes up. And we say that by saying as x approaches infinity, f of x approaches infinity. Well, what would we say for the left-hand behavior? As x approaches infinity, negative infinity, as x goes to the left, negative infinity is to the left. What does y do? Does y go up or down? Well, when I'm looking at this, the more to the left I go, y goes up. So that would be f of x approaches infinity. So as the value of x gets extremely negative, the value of y will get extremely positive. As x gets extremely positive, y also gets extremely positive. So we know this is an even function. As x goes left, y goes up. Boom. Alrighty, so when we come back in the next video, you know what? Why don't we do it here? So which of these graphs, or which of these equations, which of these functions comes from this graph? Well, even powers, remember, even powers go make a parabola of some kind. And because it's positive, we need our graph to look like this. As we take, because we can ignore everything after the first term. As x gets extremely negative, let's take a big negative value, a negative, and raise it to the fourth power. A negative raised to the fourth power is a positive. A positive raised to the fourth power is a positive. So C is made by the function f of x. G of x, let's put in a negative value. A negative, ignore all of this. We're just looking at the first term. Take a negative value, raise it to an even power. That's a positive. Turn around and make it negative. So as x gets small, y gets small. X goes to the left, y goes down. What happens if I have a positive value? Positive raised to the sixth power is a positive. Turn around and make it negative. Y is going to get negative. That's this graph. An odd numbered power. So as x goes negative, cube of negative, that's a negative. That's a negative. So as x approaches negative infinity, y approaches negative infinity. This graph looks like that. My odd power. This is h of x. Odd powers, but then we're going to make it negative. Look like this. As I take a negative value, I'm going to make it incredibly negative. I'm going to make it negative. To the seventh power is a negative. Times it by a negative, that's a positive. That's why as x is on the left, that's my negatives, positive y. All right, that last one might have been a little tricky, but if you got questions, please come to class ready to ask those questions. And I will see you when we see you in the next video when we do our graphs. So happy, have a good one, and I'll see you in class.